So far we have looked at venturimeter and orifice meter, where the main mechanism on how you actually measure the difference, measure the velocity change, measure the flow rate, measure the mass flow rate, is actually by the difference in pressure, right? So you have at point A and point B, so you mount a manometer, and based on the pressure difference, you can actually use the equation and find the value of velocity. And you can actually find the value of flow rate. So the main idea, if you see here, is that we want to measure our flow. So rotameter is another type of meter that is used to measure flow rate, in which pressure drop is constant, but the area to which the fluid flow varies with the flow rate. So if we can say that for venturimeter and orifice meter, it is dependent on the pressure difference. But when we're talking about rotameter, it is dependent on the area difference. That's why in the beginning of the class, I did mention that rotameter is a variable area meter, meaning that based on the changes in the area of the rotameter, you will have a different flow rate. Okay, so a rotameter is usually constructed from a tapered glass tube and a float of some sort. So tapered meaning here is that it will not be a straight. So if you see here, this is just a drawing of a side drawing of a rotameter. So if you see here, the size here from this point and this point is not the same. From the bottom and the top is not the same. Meaning that, so this is what we call, so if I were to draw a straight line, even though this is not a straight line, but if I were to draw a straight line, you can see here, this is how it was supposed to look like. But you have this area here, right, that is changing based on the height of the rotameter. As higher I go, the area is bigger. So this is this area, the change in the diameter from this point to this point to this point to this point is what we call a tapered glass tube. So it will have a small increment as it goes higher and higher. Okay, so that is the meaning of tapered glass tube, and has a float of some sort. So this is the float. This is what we call a float. So initially, when there is no flow, the float will be here. So I will show you what happens in terms of the forces acting on this float. Right? At a certain flow rate of the float will rise to the tube to a fixed height. At the different flow rate, the float will height to the different height. Right? So if you have a different flow rate, so it will be at a different position. And based on the position of the float of this thing, this is what we call a float, you will measure what is your flow rate. And then another big difference between venturimeter, orifice meter, and your rotameter is that rotameter must always be installed vertically, meaning that the flow will be from down to up. For your venturimeter or orifice meter, this can be your this is your venturimeter, right? So the flow is horizontal, right? This is horizontal from left to right or right to left, depending on your arrangement of the piping system. But for rotameter, the flow must always be from the bottom to the top. Okay, so this is a little bit of the explanation on how a rotameter usually works. So at point C, so this is at point C here, when there is no flow. So you can see here the taper is very small. So usually it's very small here. So this is the taper value. So initially there is no, usually the size of the diameter of the float will be the same as the diameter of the inlet. So at point C here, in the beginning, the drag force plus the buoyancy force is equal to the gravitational force, which is the weight. So usually when we are talking about equilibrium, so there will be three forces acting on a float. So if you have the float here, so gravitational force will always act downwards. So this is your gravitational force. And then whatever is acting upwards will be, one is your drag force and another one is your buoyancy force. Drag force is because of the movement of fluid that is pushing your fluid to move, and your buoyancy force is because of the buoyancy of your fluid. Usually the fluid will be made with something that is buoyant. So at point C here, if you see here, nothing is happening, it is not moving, right? Because all the forces cancel out each other. So this is actually your gravitational force, this is your buoyancy force, and this is actually your drag force. So if you see here, rho F Vf times your G. So rho F here is the density for the fluid, Vf is the velocity for the fluid, and G is your gravitational acceleration. So this is actually a way for you to write the equation for force, right? If you remember, F is equal to ma. This is one of the earlier equation you see for force. So if we just change A to G, right? A acceleration. So in our case here, G is our gravitational acceleration because we are looking at it in terms of the gravitational force. And M here is actually density times your volume, right? So if you have rho is equal to M over V, so M here is just rho times V. So this is how we get the value of this one. So the same goes here for your buoyancy force. So buoyancy force, if you see here, this one, rho F, Vf, G. For this one, it's rho, Vf, and G. So I said that the buoyancy force is actually related to your fluid that is pushing your fluid upwards. So that's why here, instead of having the density of the fluid, we have the density of the fluid here. So rho here depends, it is the density of your fluid that is pushing your fluid upwards. And Vf is the volume of the fluid, and G is the gravitational acceleration again. So for the drag force, it is actually a complicated. So it depends on the velocity of the fluid that is causing it, and CD is the drag coefficient, AF is the area of the fluid, rho is the density of the fluid divided by 2. So when you have things in equilibrium, meaning that whatever force is acting downwards is equal to the force acting upwards, your fluid will not move. So this can happen either when you have no flow. When you have no flow, so this term will be 0. So you will have your buoyancy force is equal, the gravitational force is equal to your buoyancy force, right? So at point C, in the beginning, when there is nothing, no flow, so it will not move. So when the fluid starts to flow at the bottom, right? When the fluid, when you open the valve or something, you will have fluid flowing from the bottom. The drag force plus the buoyancy force will be greater than the gravitational force, meaning that the force acting upwards here is more. So because it is more, then it will push the fluid from point C to point B. It will start moving, moving, moving. So you will have flow. So meaning that the drag force here will be greater than your gravitational force. So the amount of force that is acting downwards is lower than the amount of force acting outwards. So that's why your fluid will be going up. The fluid will start to move towards point B. So at point B, so how will the fluid stop moving at any point on your rotameter? So it will start moving again when you have this equilibrium again. So once you have reached the equilibrium based on this speed, once the speed is constant, everything is constant, so the fluid will reach to a point of equilibrium where you will have this condition again. Remember, initially you did not have this condition, but after that After a while, when it points in equilibrium, the fluid will be at the position when the drag force plus buoyancy force is equal to the gravitational force again. And this system is called to be in equilibrium. Equilibrium meaning that, again, the force acting downwards is equal to the force acting upwards. And then it will move to point A. The float has reached the maximum, the highest point in the rotameter. So maximum flow rate is achieved. So that's why when you look at a rotameter, so this is an example of rotameter, right? So you will have a scale. The scale is usually will be here, okay, on the rotameter. So based on the position here, based on the position of the float, usually something like this. So you will read. So maybe this one is, if I follow this scale here, is around maybe 76 or 77. Now, the maximum I can go here is 100. So if my float here is at this point, so I know that this is the maximum flow of my rotameter. So if you see here, the rotameter can come in different shape depending on how much flow you have. So if you have a flow up to, let's say, 1000 meter cube, right? 1000 meter cube. So you will have a different scale. So these are some examples of how a rotameter will actually work. So you can have a small one. We can have 0 until 1 ml, or you can have 0 until 1000 liter, depending on the your flow rate. So, and you can see here, you can have different shape of floats, the shape of the float. So the way you read is that, if you see here, this one is usually for a liquid, and usually this one is usually for a gas. So you can see here the scale here. So if, let's say, your float is around at this point, so this is the value of your flow rate. Okay, and then this one again, a different type of rotameter. So you can see here, this is actually a 3D view of a rotameter. You can see here, flow will come from here, and then it will go up, the rotameter will go up until the float reaches equilibrium. So you can see here, there will be a value here where you can read it. And you can see here, the diameter initially and the diameter at the top is a little bit different because of this taper value. Right, so you will have a taper coefficient to decide how much is the angle of changes. Okay, so that is how the mechanism of rotameter, that is how a rotameter works.